So what we have here, we've done and learnt a fair bit of strategies so far for permutations. We've learnt the spaces technique for the fundamental counting principle, and we've learnt some stuff with identical objects. What this set of notes will do, will review some of the concepts we already know, and it will also fill in a few of the strategies that we haven't looked at completely yet. So this is our additional notes. Now, counting, the study of counting is something called combinatorics. That's just the fancy word for it. And we're going to look at some extra examples. So the first thing that we've already learned is the fundamental counting principle. This is our spaces. We remember that we draw a space for every decision that we have to make. So in this example, for the new car, the owner has 3 decisions. So we would draw 3 spaces for this, and we would write a little note underneath each of these spaces. This is going to be my color choice, transmission, and interior. So just a little description of what our decision was, and then the number that goes into these spaces, how many choices we have. How many choices of color do we have? 3. 2 choices of transmission, 2 choices of interior. Multiply those all out, and we'll get 12. Now we could do this with a tree diagram as well, but the spaces technique allows us to get the total amount probably in the quickest way. So we can do spaces questions with numbers, and sometimes you'll find questions say certain numbers can be repeated, means that they could be used more than once, and other times they're saying that that list of numbers is a set of objects and you can only use each object once. So if we were allowed to repeat things, we'd have 3 decisions to make because there's 3 numbers in a 3-digit number, and we would have 7 choices for our first digit using the numbers 1 through 7. And if you're allowed to repeat, you'd still have 7 numbers for the second one and 7 numbers for the third one, for 343 in total. But if you weren't allowed to repeat, if we're imagining those are actual objects and you have to use those numbers that are there, then there would be 7 choices for the first one, and one of the numbers would be used up. And then you would have 6, and then you would have 5. And when you're using up objects, this is called a permutation. And so you could write this one as 7p3 if you'd like. But for the most part, when we do permutations, we use a lot of spaces to figure it out. A reminder that this formula is 7 factorial over 7 minus 3 factorial. That's how that formula works. Basically, this 3 tells you how many spaces you had, and the 7 is the number that you started with. Now, this example is something a little bit new. So again, how many 3-digit numbers? I'm going to still use the numbers. So add this in. We're still going to only use the numbers 1 through 7 without repetition. So it's like those are objects. You can use each one once. And it says how many 3-digit numbers are even. So now, not only do we allowed to use the numbers 1 through 7, but we know that our last digit has to be something to make it even. And this is a restriction on our set of numbers. And we haven't done a lot of questions with restrictions yet. Now, the main strategy with a restriction is we have to deal with that restriction first, which feels kind of weird in this question because it's our last digit. In a 3-digit number, the even, to make it even, means that our last digit here is the restriction. And up till now, we've always done the last digit last. So this is a little bit different. Now, using the numbers 1 through 7, can you see that the only even ones are 2, 4, and 6? So when we write our description, we sometimes want to be really specific in what we're writing here, that the last number can be a 2, a 4, or 6. So how many choices do we have for that? 3. So this is the first number we would put into our spaces. Now, there's no restrictions on the other 2 digits. How many choices do I have for my first digit? 6. There was 7 to begin with, but you've used up either a 2, a 4, or a 6. And then, how many choices for the middle digit? 5. This gives us 90 in total. Now, what happens if we didn't deal with that restriction first? Because this is what often tells you that you need to look at your strategy different. Is if you try one strategy and then something runs into a problem, it may mean that you need another strategy or need to look at it different. So even if we know that this is even, but you say, well, I'm going to start with my first digit. How many choices would I have? 7. And then I would have 6. And then you might be tempted to write 3, because there's 3 even numbers. But what happens if in your 7 you happen to choose the 2? Then you wouldn't have 3 choices for the end. You would have 2. So it could be 2 choices here. But what happens if in your 7 you chose the 2 and in your 6 you chose the 4? Then you might have only 1 choice here. And we don't know what number to put in there, because it all depends on what your choices were here. Yes? So in this one, when we deal with this first, and we have our 7 numbers, it means we are either going to choose the 2, the 4, or the 6 first. Whichever one we choose, say we chose the 4, now how many choices are there left? Now there's only 6 choices left for that first digit. And say you chose the 7 as your first digit, now there's only 5 choices left. If we show this as a tree diagram, it's going to be a little bit messy, but sometimes seeing it as a tree diagram helps. But first, I want to put a big X through this, showing that if you didn't deal with the restriction first, you run into a problem, because you don't know what number to put in that last space. And you might be tempted to put the 3, but it might not be a 3, depending on the number you chose. So as a tree diagram, this is what's happening. We're figuring out our last digit first. It can be a 2, a 4, or a 6. If you chose a 2, now we can go to our first digit. Does it make sense that if you chose the 2, your first digit could be a 1, a 3, a 4, a 5, a 6, or a 7? You just can't choose the 2. If you chose the 4, it could be, oh, is there not 1, 2, 3, 4, 5, 6? There we go. It could be a 1, a 2, a 3, a 5, a 6, or a 7. Just the 4 wouldn't be. And if we chose a 6, it could be a 1, a 2, a 3, a 4, a 5, or a 7. Okay? This is where things get messy, because now to pick your second digit, and I'll just do this one. 1, 2, 3. Wow, that looks ugly. Let's try that again. 1, 2, 3, 4, 5. If we chose the 4, then the 5, what are our choices that it would be left? A 1, a 2, a 3, the 4 is gone, the 5 is gone, a 6, or a 7. That's why there's 5 choices left for our second digit. Now, this would have to be repeated off of each one of these. Wow. So it's supposed to look like it's getting messy. There we go. Right? There would be a lot of these. Something like that in the end. And you could write all those numbers out, but your tree diagram would have 90 things in the end. So this is why a tree diagram is not necessarily a good strategy for these ones. But sometimes by doing a tree diagram, at least for part of it, we can see why the numbers change. Like now that you see, if I do my last digit first with a 3, and I have a 2 there, I can see why there's only 6 digits left here, or 6 digits left here, or 6 digits left here, and why we put a 6 in that second spot. So I want you to do this, example 5. No, that's not the one I want you to do. Example 4, again, using the numbers 1 through 7, but now I want you to figure out the odd ones. And once you've got your answer in one way, I want you to think about it and see if you could get the same answer using a different strategy. For the odd, how many people started their strategy by making 3 spaces? And then writing odd in here, maybe even writing out what the odd numbers are, because that's our restriction. So we had 4 choices. And then how many choices for the first one? 6, because you've used up a number, and then 5. For 120 in total. Did anyone find a second strategy? What's that? You drew it. Well, tree diagram, okay, that would be a second strategy, but it would be sort of the same idea strategy. Wonder if there was a different idea strategy. You could use, okay, in number 2, we figured out all the numbers from 1 to 7 without repetition was 210. And then in number 3, we figured out that the even ones were 90. How could we get the odd ones? We would subtract. Now, this strategy, I even have a name for this strategy. I call it the NOT strategy, N-O-T, because it's a strategy where you count what you're not supposed to, and you count all of them, and if you subtract the ones you're not supposed to, the bad ones, from all of the ones, you'll be left with the good ones. So in other words, if I want to find the odd ones, I could count the even ones and subtract it from all of them, and I'd be left with the odd ones. Now, in this case, there was no real benefit to doing that. In fact, from the beginning of the question, this technique, what we did with the restriction, is probably the quickest and the easiest. But we will get some questions where this NOT strategy will be the best strategy, because it will be easier to count all of them and the bad ones than it will be to count the good ones directly. So that strategy is going to come back. Try this one. There is a restriction on this one. Can you find it? All right, quick check. Restriction is on the first one. It can't be 0. So how many choices do we have for our first one? 9. Because there's 10 digits in total. And then one of our numbers has been used up, but 0 could get put back in, so we have 9 again, and then 8 for 648. The last thing we're going to do is just a little bit of practice with factorial notation, mental math. What's the first one? 42. Again, we can simplify factorials by expanding the bigger one until we get to the smaller one. So we get 42. A little bit more mental math. Okay. Again, I would expand the biggest one, so that's going to be 10 times 9 times 8. And I would keep going until I get to one of the factorials on the bottom. I'm going to expand the 4 factorial as well. So my 6 factorials could cancel out. Are you okay with canceling out the 8 with the 4 and the 2? And then the 9 and the 3, if they cancel or simplify, I'd still be left with a 3 on the top. Yeah, I can do that again. Zoom, 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 zoom. There we go. Okay. First of all, I expanded the big one, right? Are you okay with that? And I stopped when I got to 6 because it would keep going, and that allows me to cancel these. Choo, choo. Okay. I expanded the 4 factorial to get 4 times 3 times 2 times 1. And 4 times 2 is 8, so those cancel out. Now the only number I'm left with on the bottom is the 3. Since 9 divides nicely by 3, I can cancel those and I would be left with a 3 on top. So now what are the numbers I'm left with? I've got a 7 on top, the 3 on the top, and the 10. 210. Now, with variables, again, same idea. We have to find out which is the biggest. Is n plus 2 or n bigger? So we start expanding the bigger one, always subtracting by 1 each time until we get to the one on the bottom, because then we can cancel them out. So we're left with just n plus 2 times n plus 1. You could, or you could leave it. You could leave it as n plus 2 times n plus 1. There'll be some questions where it'll make sense to write it as an expanded form, depending on what the question is. If the question was, like if it was solve for n, and this was equal to 72, okay? Then you would have this equal to 72, and you can't solve that unless you expand it and then move the 72 over to the other side so you could factor and solve. So in that case, you would have to expand it. What if the bottom is bigger? All right, this is the number one place where students make mistakes in figuring out which one is bigger, right? They see the 3. They see the 1. They say 3 is bigger than 1. And so they think the top one is bigger. But if you're ever wondering, you can plug a number in. Like if I plug in 8, you see the top would be 5, the bottom would be 7. The bottom is bigger. So we start expanding the bottom one. What's one less than n minus 1? N minus 2, and 1 less than n minus 2 is n minus 3. And then these ones would cancel, and you would be left with 1 over n minus 1, n minus 2.